Yach. Sorry about that. Okay. So, this week we're going to start again with the aerosols part of the course and try to learn a little bit more about the nature of atmospheric aerosols. So, this simulation is the result from, well, it's an uncoupled simulation of aerosol optical depth. Do you know what I mean by uncoupled in a model?
Yeah, you run the climate model first and then use the atmospheric field to simulate the movement of aerosols.
You run a climate or a weather model first, and you then use that to drive not just the transport, but also it can be the emissions and the chemistry and the processes of aerosols. And so this simulation is depicting the aerosol optical depth. So when we talk about the aerosol optical depth, what are we talking about? Is this the surface concentration? Is it the concentration of aerosols at a particular height? It's the column integral of the optical depth of the aerosol. Yes. So, the different types of aerosol in this simulation are coloured. What do you think the blue coloured aerosol are in this simulation? Sea salts. The green coloured, they are organics, but in this case they're from fires rather than from the biogenic emissions from forest. So these are from forest fires and biomass burning. What about the red, the orange? Sorry. Okay, so they're dust. And the white? So anthropogenic. So in this simulation they're saying that they're sulfates predominantly. So what can you say about the various source regions? So they're carbon from fires. So what you can note about the sea salt, why is the sea salt predominantly shown in the bottom part in the southern hemisphere there? So yeah, you're in the roaring 40s. So the roaring 40s, really, really strong winds north of Antarctica, and you get a really clear fetch over the oceans, and the sea spray is wind driven. So you've got China, Europe and the US there with the fossil fuel sulfates. And you'll also see fossil fuel sulfates emitted when volcanoes erupt, and there's an erupting volcano later on in the simulation over Madagascar. But you see the transport of dust, which is very seasonal, across from, so these are fires in the equatorial Africa mixing with the dust and being blown right across to the US, or South America in this case. So it's a very complex pattern of different sorts of aerosols being moved globally. So, yeah, there's the Madagascar volcanic eruption will be coming up now. So, do you know where Madagascar is? Just there, where the hot spot, and you can see that it's dominating the emissions of sulfate in that particular part of the simulation. So in order to capture the various circulation patterns, no problem. In order to capture that, you need to know something about the sources. And this lecture will be predominantly around saying something about the nature and behaviour of atmospheric aerosol. So, what I'll do we'll start off with a quick recap of what we did last time and the main points that we were covering, and then move on to saying something about the sources and the nature of atmospheric aerosol. So, last week, or the week before last, we talked about why we studied aerosol. And there are a couple of main reasons: the health effects, and there's an indication of the primary first evidence for health effects from aerosol in the London smog, photochemical smogs, which were happening in summertime oxidative conditions rather than wintertime anticyclonic conditions, and the particles can enter down into the airways further if they're finer. And then the second reason that we're looking at atmospheric aerosol is because of their radiative forcing, and so here we've got the indirect and direct effects from aerosol being shown, offsetting, if you look at the largest error bars here, potentially the warming from the radiatively active gases. And aerosol optical depth, you can see here, hotspots according to the source regions, and we've just seen that from the video before. And we need to take care when we're attributing the various scattering and forcing components because of discrepancies between model and measured results, where if you make the wrong assumption about what size particles are made of what components, you can come up with the wrong calculations of forcing. So we touched a little on the different sorts of interactions between particles and radiation, and diffraction, Raman scattering, fluorescence, reflection, different scattering, the mass extinction efficiency and the single scattering albedo affected by the refractive index of the particles, and then the indirect effect caused by the activation of different aerosol particles into clouds. And then, illustrative of the complexity of the sorts of effects of aerosol, this picture here was just to depict how variable the different components of the indirect and direct forcing will be. So we've just seen that video and shown that there are a whole load of different sources in different regions, which mean that you end up with a different sort of mixing of different components in the atmosphere. So in order to make those sorts of simulations, you need to know something about how strong the sources of the different aerosols are. So there are two main distinctions, primary and secondary aerosols, we've learned already. So primary is direct injection in the condensed phase. So what's the condensed phase? Liquids or solids. Okay? So you can have direct injection of, give me an example of direct injection of liquid particles. Sea spray, water, and it's an injection into the atmosphere of liquid particles because of the wind-blown generation of sea spray. Of solid particles, dust, or resuspended road dust or soil, or pollen even. So primary is the direct injection of the condensed phase. Secondary is an injection of gases that can form particles in the atmosphere. So if you have particles that are sea salt and you condense some, if you have some sulfur dioxide in the same air that then gets oxidised to sulfuric acid and condenses on the sea salt, are the particles primary or secondary? Part of them is primary and part of them secondary. If you now, do we know what things are if we just measure them? Is there a detector for primary particles and a detector for secondary particles? We need to know something about the sources, because it's very, very difficult, just from the chemical composition, to infer whether the particles are primary or secondary. There can be some evidence, because we don't know of any source of black carbon that is secondary, and we don't know of any source of nitrate that is primary. And so generally you can say, when you're detecting them, that things can be likely to be primary or likely to be secondary. But it's very difficult. There is no such detector for just primary particles or secondary particles. What are combustion particles? Are they primary or secondary? Who thinks they're secondary? Who thinks they're primary? Well, it depends where you're actually measuring them. So how are combustion particles formed? From combustion. But they're formed, let me just see, yeah, I'll come on to that afterwards. So combustion particles, you normally call them primary because you normally measure them after the tailpipe or after the exhaust pipe or after the chimney stack where they're emitted. If you actually measure them in the combustion chamber, they can be gases and then they condense to form particles. And so they can be considered secondary if they're in the combustion chamber, and they can be considered primary if they're measured after the exhaust. So primary particles. Let's go through the different sorts of primary particles. So as we say, they are direct injection or emission of the condensed phase into the atmosphere. So dust. Is there a lot of dust in the atmosphere? Well, it depends where you are. If you're over the ocean, generally, there's not too much dust unless you're close to a continent with erodible surface. We've seen that the Sahara, there can be a lot of outflow of dust over the Atlantic Ocean. But if you go down into the Southern Ocean, there's almost no dust. So the aerosol optical depth contribution from dust is very, very variable. Why is it variable? There's two parts to the equation. You need to be close to the source, and secondly, dust. Are they fine or are they coarse particles? Coarse. So how long do they live in the atmosphere? They're short, yeah. They're shorter because they're larger and they can settle out. Okay, so the lifetime is generally shorter, unless they're elevated very, very high, and then it can take more time for them to settle out. But generally, dust are coarse particles, so they don't last for very long, so you need to have a continuous source of them in order for them to be in the atmosphere. This means that they can be localized. They're not generally globally well mixed. So if you look at the top left figure, there are multiple ways of generating dust particles. So creeping means that the wind speed is not sufficiently high for the particles to be lifted. So the particles are just moving along the ground. Once you get sufficient turbulence, so the roughness of the surface is sufficiently large and the wind is sufficiently high, then you can end up with a bit of lifting of the soils. Once the particles are lifted, they collide with the surface again, and you end up with kicking up of more dust. So there's a wind speed dependence upon the generation of dust. The higher the wind speed, the more you can induce these collisions at the ground, and the more dust is injected into the atmosphere. So the flux is related to the wind speed via the shear velocity and the soil type. So is a clay type soil more or less likely to give rise to dust than a lower clay content? The clay tends to bind. So if it's much looser mineral content, then you tend to be able to kick up more dust. So the soil type and the wind speed are both important. So when you have atmospheric models, they consider the soil type, the soil moisture content, and the wind speed, and that tells you something about the source flux of the dust. So if you look at the map on the bottom right-hand side, you can see the strength of the annual mean forcing of soil dust. So why would you suggest the pattern that you can see is there? Have you got any idea why the soil type is different between the deserts over northwestern China and the desert in the Sahara? Is it windier in China? It's the soil type. It's purely because of the distinction between the different types. Okay, it's not a meteorological factor. So the desert, you've got this very, very strong dependence on the soil type of the forcing, of the emissions and the forcing. Sea spray. So that's direct injection of liquid. So the condensed phase here is liquid. And there are three main mechanisms that all happen as a function of wind speed. So the biggest particles formed at low or high wind speed. It's high because they are ripped off the waves when it's very high wind speed. But under lower wind speed conditions, almost all the particles from sea spray are formed not by direct ripping of the water droplets from the sea surface, but they're formed by bubble formation. So what happens, excuse me, is that the air gets folded into the surface of the liquid. So you end up with white caps. So you're familiar with the expression white caps. White caps is, if you see from space the surface of the ocean, you can see that when it's very, very windy, you can see that the sea looks white rather than just blue. So that's because of the bubbles. The bubbles give rise to the white capping. Those bubbles can then burst, and if you see the figure on the top left, when the cap of the bubble bursts, the bubble itself turns into many, many millions of very tiny particles. But also, when it bursts, it sucks up a jet from the bottom. So that jet there is caused by the change in pressure when the bubble cap bursts. And it pinches droplets They're shot up from the jet. So the film drops are the very finest. The jet drops are the ones in between. They're around 10 microns in diameter. And the spume drops, they're the ones that are ripped off the top of waves. They're very large, up to about 0.5 millimetre or a millimetre or so. You can feel it when you're in a very, very windy conditions near the sea. They are the spume drops. So which ones last the longest? Film drops, because they're smaller. So the spume drops, they only last tens of metres because they settle very, very quickly. The smallest jet drops and the film drops can last for up to a couple of days. And the very finest film drops can last even longer. But they're never injected very high in the atmosphere, so they never have, they can never be enhanced in their lifetime in the same way as dust. Dust can be injected quite high in the atmosphere if it's caught in an atmospheric conveyor belt to lift it, to elevate it in the atmosphere. But sea spray is only ever a low-level phenomenon. The dash line's there?
No, on the, yeah.
On here? Sorry, I need my glasses to see the dash lines. Right. Those, let me have a look, primary marine aerosol flux, yeah. These are calculations of the, if you look at the units here, primary marine aerosol number flux. So this is the number of particles per square metre per second. Okay, this is millions of particles per metre squared per second. And this is related to the wind speed, and these are measurements that are made from a ship. And so each of these triangles is an observation of, do you know how you measure the flux? Does anyone know? Eddy covariance is the most direct way of measuring a flux. Eddy covariance, eddy correlation. You can have something called relaxed eddy accumulation. Is anyone familiar with these techniques? These are micrometeorological techniques. You measure how strong the upward and downward components of velocity are very, very fast. And you measure at the same frequency how high or low the concentration of the particles are. That's eddy correlation, yeah. But that's eddy correlation, eddy covariance. Relaxed eddy accumulation is if your sensors are not quick enough to measure the particles at the same frequency. So what happens is that you measure the wind speed up and the wind speed down, and you control valves very quickly, and you accumulate the measurements of the particles in all of the updrafts in one set of measurements, and in all of the downdrafts in another set of measurements. And so that is a much longer term sort of measurement. Relaxed eddy accumulation is for when your instruments are less sensitive. And so certain instruments are sensitive in the right region for measuring very fast, and certain instruments can't measure so fast in other sizes. And so you need to combine eddy covariance and relaxed eddy accumulation to measure the fluxes. And so these are error bars, if you like. So the dotted lines are essentially capturing the if you look here, if you just fit a line, the best fit line through all of these fits through the middle. These capture the trends with some level of uncertainty, but basically you don't know much better than these dotted lines where the true flux lies. So that's what they are. They'll be confidence levels.
So we've got dust as a function of wind speed, sea spray as a function of wind speed. So they're primary components. Now combustion-derived particles. Now the reason that it's difficult to say whether they're primary or secondary is that under hot conditions, the components that give rise to the particles are gases. And if you had complete combustion, for example, methane combustion would go just to carbon dioxide plus water. But you never get complete combustion. It's just not possible within the efficiency of any combustion units to get complete combustion. So you end up with a lot of radical chains. Now the methyl radical, acetylene, propargyl radical, phenyl radical, etc., they can condense and they form aromatic compounds and polycyclic aromatic compounds. And are these gases or particles? Are these condensed or are they gases? Where are they particles? But where are they particles? Are they particles inside the combustion unit? At 500, 600, 700 degrees. They tend to still be, they can be partitioning between the gases and the particles at very high temperatures. And then by the time they get to atmospheric temperatures, they're in the particles. So you're right, by the time we sample them from combustion units, the polycyclic aromatic compounds are very much more likely to be in the particles. But you can still get some of the smaller polycyclic aromatic compounds as gases. So if you've just got two, naphthalene or pyrenes or whatever, some of those still partition even at atmospheric temperatures between the gases and the particles. But the very largest are all in the particles. And what sort of particles are these? Does anyone know how they're normally referred to? They're normally just called soot. So soot is just a collection of the chemical condensation products of incomplete combustion. So chemical condensation gives rise to larger molecules that give rise to soot particles. So we've got our primary dust, primary sea spray, and our combustion-derived particles. And what happens in the atmosphere is they all get mixed up. Now we saw from the simulation right at the beginning that whilst you've got regions of the planet, so you have the roaring 40s where it's mainly sea salts, you have the Saharan outflow where it's mainly dust, the industrial regions where it's mainly industrial emissions, including the likes of sulfates, etc. Biomass burning regions where it's mainly biomass burning. But you get mixing of the components wherever you get air masses that are interacting. And so you end up with really quite complex morphologies, composition and size. So here, these are a bunch of offline analyses that just show how you get the different components. Down here you've got sodium chloride, so you've essentially got sea salt on top of dust. Excuse me. Up there you've got different soots that are lumped with different non-fractal components. And up the top you've got sulfates with sodium chloride. And so when you get condensation of gas phase sulfuric acid onto sodium chloride, you can end up with sodium sulfate. So you get chemical reactions that mean that your original primary components plus your secondary components can give rise to a product that wasn't actually either initially emitted or wasn't condensed. So you get quite a lot of complexity in the real atmospheric aerosol that you're measuring. And there's a few more examples, just giving you ranges of the size of the particles that you're finding. From diesel soot around 0.1 micron, but here you've got, well, the primary spherules are about 0.1 micron. So the primary components that make up the chains are of the order of 100 nanometers, going up to pollen, which can be up to about 1/10 of a millimetre. It's not only man-made pollution that gives rise to haze. I don't know if have you got examples in China, but you certainly have examples of the Blue Mountains or the Red Mountains in the US and in Australia and the likes, where you've got natural emissions of VOCs that give rise to hazes. So you can get photochemical smogs over forests. So what are the required ingredients for photochemical smogs? And sunlight. Yep, so you need the energy, you need some background NOx level, and you need some VOCs. And you have masses of VOCs. Do you think there are more VOCs from natural sources or anthropogenic sources? It's far, far, far more from biogenic sources. Lots more from biogenic sources. Do you know what the main emitted component from biogenic sources is? Main VOC? Sorry? What is the chemical compound that's emitted most? No? What's half an alpha pinene? Does anyone know what half an alpha pinene is? Do you know how many carbons has alpha pinene got? C10H16 is alpha pinene. So what's half an alpha pinene? C5H8. Okay? C5H8 is isoprene. So isoprene is the biggest, is the dominant emission, and it's the biggest emission, the biggest emitted VOC. So what happens is these volatile compounds, through oxidation, can lead to nucleation of new particles. And they're very, very fine. In fact, they're much finer than this diagram actually shows. And we'll come on to that in the next couple of slides. Or these same molecules can condense onto the pre-existing primary or secondary particles and get converted. So we saw the example before on the previous slide where sea salt plus sulfuric acid can lead to sodium sulfate. So heterogeneous chemistry can take place. So not only can you just move from the gas to the particle, you can also have chemical reactions in the particle. So the secondary aerosol mass, there are a few compounds that will move from gases to particles. What is the dominant characteristic? What is the property, the main property, that moves things from gases to particles? Saturation vapor pressure. So what is a saturation vapor pressure a measure of? Well, I know it's vapor pressure, but what is the general term? The volatility. Okay? So the volatility, I mean, I always give the example, and I think I might have said it or might have asked already. If you have oil, water, and gasoline in 3 beakers, and you left them there overnight, which one would have most? If you had the same amount, or the same volume of liquid, which one would be fullest in the morning? And which one would be least full? Gasoline. Okay? Because the oil is least volatile, water is the middle volatility, and gasoline is the most volatile. So which one's got the highest vapour pressure? Gasoline's got the highest vapour pressure, and the oil's got the lowest vapour pressure. So volatility high, vapour pressure is high. Okay? So involatile components readily partition to the aerosol. So how do you get involatile components as gases? We've already said that involatile components want to be liquids or solids. So how do we get things that want to turn into particles? Well, you either reduce the temperature or you reduce the vapour pressure. So how do you reduce the vapour pressure of a gas? Without reducing it at the same temperature, how would you reduce the vapour pressure?
Reduce the gas.
Change the gas. So you can, if you can change the volatility of the gas, you would have, if you chemically react the gas to make it more volatile. Now, if you add oxygen to a gas, then it reduces its vapour pressure. So, involatile components readily partition to aerosol from the gas. Semi-volatile components, they carry on moving between particles and the gas if they can't make their minds up. So, something like nitric acid. Nitric acid wants to live in the gas phase or in the particle phase. And so, if you warm the air up, your nitrate particles can turn into nitric acid and ammonia. And if you cool the air down, then the nitric acid and the ammonia become nitrate particles. Sulfate is much, much less volatile. So sulfate particles, they want to stay as particles. They don't want to be gases. So if they're made in the gas phase, they want to condense. So nitric acid carries on moving between them because it's semi-volatile. Sulfuric acid just goes to particles. So if you oxidize sulfur dioxide and turn it into sulfuric acid, and it sees particles, it will condense. Even if it doesn't see particles, it will make new particles. If you have nitric acid and it sees particles, it makes its mind up and it decides, depends how hot it is, whether or not it moves to the particles or stays as a gas, because it's more volatile. So what about hydrochloric acid? Is that semi-volatile or is that involatile? It's slightly more volatile than nitric acid. Okay, so it wants to be a gas more than nitric acid. So, is there anything else? Any other acid I can think of? Does ammonia want to be a gas or particle? It depends how much acid there is in the atmosphere. If there's a lot of acid, ammonia wants to be in the particles because the vapour pressure of, say, ammonium sulfate is very, very low. And so ammonia on its own has got quite a high vapour pressure, but when it reacts with sulfuric acid to form ammonium sulfate, it's got a very, very low vapour pressure. And so chemical reaction will lower the volatility in the gas phase or in the condensed phase. So we mentioned that if a gas sees a particle and it's low enough volatility, then it will condense and it will move to the particles. What happens in the atmosphere if you don't have particles? What happens to those low volatility gases? Okay, so if something has a greater abundance than its saturation vapor pressure, it gets to a supersaturation. How much supersaturation does it need to form new particles? It depends on what? It depends on the temperature. It depends on the energy barrier that's actually required to make the new particles. So if your supersaturation isn't high enough to get greater than the energy barrier to form the new particles, so if you look here on that Gibbs energy plot as a function of radius, if you can't get above the hump, you can't form particles. So you just fall back down onto the gas phase side. So you will increase the delta G by increasing the supersaturation. But if you don't get higher than the energy barrier, you won't form new particles. However, if you do have enough, and in this case it was sulfuric acid, if you do have enough, you see these particle bursts. And is everyone familiar with these bursts of particles, these nucleations in the atmosphere? So nucleation is shown, we measure nucleation by measuring the size distribution of particles as a function of time. So here you've got the particle diameter, and the colour, the hottest temperature, is the number of particles. You can see here at the beginning, you've got particles around 3 nanometers in size. So this is when your supersaturation has got high enough to overcome this thermodynamic barrier and form particles. And these particles form, and they're detected here at around 3 nanometers. And they start growing because you've got something now that you can condense the gases on. These particles start growing up to the range of 10 nanometers here, up to about 100 nanometers. And if you look, these are a couple of studies from Beijing, because this is a place we do quite a lot of work at the moment. So we've been involved in a couple of field projects over in Beijing. And one of the first year-round studies, in 2005 this was, so it was reported in 2007, showed different types of nucleation bursts. So you can see here the very low sizes, the particles are growing quite slowly. In this case, very low sizes, the particles are growing very, very quickly. And that's just an example of particles in a year-round study. In here, this was an Australian team that measured particles even smaller than the 3 nanometer cutoff. And you see that there's almost all of the time, there are particles between 1 and 2 nanometers. But they don't always grow. But here they've grown, here they've grown, here they've grown, here they've grown. So these secondary particles are formed in the atmosphere all of the time, but they don't always grow. So why don't they always grow? Well, it's because they haven't got enough vapour to move from the gas phase to the particle phase for them to get bigger. There's always enough gases to make the very finest particles, but there's not always enough for them to grow. And here, just zooming in on one of the days, this is a whole month's worth of nucleation measurements, but here you can see that there's growth of these very fine particles, up to 10 nanometers, 50 nanometers or so.
But why there are so many big particles in the first picture?
Okay, so can anybody answer that question? Why are there so many big particles in this first picture? Those instruments are just measuring particle size. They're not saying anything about the source. So you can have lots and lots of pollution from different sources. So these aren't formed from secondary particles, necessarily. These can be direct emissions of pollution. You're talking an Aitken mode. So the nucleation mode is between about 1 and 5, 1 and 10 nanometers. This can be primary particles. Okay, so these can be primary emitted particles. Yep.
That's not in the second figure.
In this figure?
Yeah.
No, this,
It didn't spot any big particles.
in this one, you can see that there's some pre-existing particles here. Yep. Now, what happens is, this is quite complex, but if you suppress the amount of bigger particles that are available to condense your vapours, it means that there's more left to form the new particles and to grow the smaller particles. And so if you've got less pollution around, less particulate pollution around, that gives you more of a chance to grow the very finest particles. Because you've taken away something called the condensation sink. So if you take away your ability to scavenge the vapours, that means that those vapours are still left to nucleate particles. So there's a competition between forming new particles and growing old particles. So we've said something about primary dust, we've said something about primary sea spray, we've said something about combustion particles, we've said something about nucleation of secondary particles, and all of these contribute to a very, very wide range of sizes, classified into different definitions. Their typical size ranges are exemplified by here for the different sorts of particles you're talking about. Their interactions, for comparison, their wavelengths of electromagnetic radiation. So what will that say actually? If your wavelength of radiation is comparable in size to an aerosol population, then that aerosol population can interact with that radiation. So you can actually, number one, it can have an impact if there's an atmospheric radiation in the wavelength that corresponds to the aerosol, but also it can be used to detect the aerosol if you want to use that in a measurement device. So this gives you a point of reference for the sizes. And a different way of showing that is this picture, which gives you a quick summary of the different sorts of particles and the different nomenclature. So is everyone familiar with the terminology there? Does anyone know, well, so the nucleation mode, that's what we saw in those nucleation bursts. The Aitken mode, that's what we saw in the pre-existing particles. So that's these particles here. So the nucleation mode, that's these particles here. So the particles that are seen there. The Aitken mode is these particles that are seen there. The accumulation mode, so we know why it's called the accumulation mode, don't we? Because it accumulates. Why does it accumulate? So why does the accumulation mode accumulate? Because it's not removed. Okay, the accumulation mode accumulates in the atmosphere. It's got the longest lifetime of all particles because it's not removed by diffusion and it's not removed by deposition. Okay, so the accumulation mode has the longest lifetime. And then the coarse particles, which are removed by sedimentation. Right, so if you remember roughly this figure, then that's pretty much all of the processes you need to understand about atmospheric aerosol. So now definitions of the sizes and how we measure and how we describe the particle size distributions. Have you come across the log normal distribution? You come across a normal distribution, just a straightforward Gaussian distribution. Well, if you turn that into log space, then the same statistics can be used just to describe the log normal distribution. And the log normal distribution is useful because the range of size of atmospheric aerosol is so large that you need to cover many orders of magnitude. So we need to do it in logarithmic space. So if you look at this here, 1 nanometer, 10 nanometers, 100 nanometers, 1,000, 10,000. We've got 4 orders of magnitude in size. So if we did that just in a normal, well, if we did it just on a linear scale, then you'd be very, very skewed in describing the aerosol distribution. So what's the surface area of a sphere? Four pi r squared. What's the volume of the sphere?
R divided 6.
4/3 pi r cubed. Yeah, so 4/3 d divided by 2 all cubed, whatever. But all you're doing when you're turning a log normal distribution in number space to volume or area space, you're just making a spherical particle assumption and using that geometry to turn from dn by d log dp to dv d log dp to dA by d log dp. So when we're describing log normal distributions, we do it according to the d log dp. So that's the bin width, if you like. The size bin width is the d log dp. Because we need to know, I mean, if you had a very, very broad size bin, then you'd have more particles inside it. So in order to make sure we're comparing one bin to the next bin, we need to make sure that we're talking about the same width of a size bin. So here are some examples of size distributions in number, surface area and volume space. So these are the same size distributions. So if you look at the top panel, you can see that the left-hand distribution has the most number. By the time you try and calculate the surface area, that first mode is almost gone, because it's dependent upon the radius squared. So you almost don't notice it. And by the time you get to the volume, that first mode is insignificant. So what does that say about the mass of nucleation, mass of particles during nucleation events? Does it matter? Does nucleation matter in the atmosphere? Well, it depends what you're trying to consider. In terms of health effects, in terms of PM, then no, it won't matter at all. But in terms of number of particles that can act as seeds that can then grow large enough to be important, then it can be important. But the nucleation mode has almost no mass. So the nucleation mode will have almost no mass. Well, and it will have very, very small surface area, but it has the most number. If you look on the top panel, there are almost no particles at all at 10 nanometers. But by the time you look at the mass, they're almost the same amount of mass as the accumulation mode in the coarse particles. So it very much depends on what you're interested in, whether or not you need to consider the particles in the atmosphere. So note in this picture here, this smallest size is 0.01 microns. So that's 10 nanometers. And this is a remote continental size distribution. And we saw earlier that there were nucleation particles in certain conditions. And in this case, these were measurements, and there is no nucleation mode. So either there was no nucleation mode formed, so why might there be no nucleation mode formed? Has anyone got any ideas about why there sometimes is nucleation and sometimes isn't? If you have no sulfur dioxide, you'll have no sulfuric acid, so you won't be able to nucleate with sulfuric acid. So if you're in a very low polluted environment, then you don't have any gases to form the nucleation mode. It's not just sulfuric acid that forms it, but why is sulfuric acid particularly good at nucleating? Because of its very, very low vapor pressure. But you can also have very low vapor pressure organic compounds. But normally it's something like sulfuric acid. But in these cases, either there weren't any formed, or the nucleation mode has been eaten up by being scavenged or evolving into the Aitken mode. So they're the Aitken particles, and they're the accumulation mode particles. The accumulation mode particles can't really grow to coarse mode particles because they just don't live long enough in the atmosphere. That would be to grow from about 500 nanometers or a couple of hundred nanometers up to 10 microns. There just isn't enough time in their lifetime to grow that distance. So just as a point of note, look at the difference between the number and the mass of the coarse and the fine aerosol. And remember that most of the particles that contribute to the mass make negligible contribution to number, and most of the particles that make the big contribution to number make negligible contribution to the mass. So here, these are linear scale. Okay? So they're logarithmic in the x-axis and linear in the y-axis. So the same as this, linear in the y-axis and logarithmic in the x-axis. This is logarithmic in both axes. The reason it's logarithmic in both axes is because we want to contrast the different concentrations in different regimes. If you look at a very near to road particle number distribution, so this is dn by d log dp, you are hundreds of times or thousands of times higher in concentration of particles than you are in the urban or the rural clean background respectively. So if you remember right back to that video of the distribution of the aerosol optical depth globally, if you compare where the AOD was high because of a source and somewhere where there were no particles, you can see that this sort of thing is borne out, that you've got hundreds of times more concentration of particles when you are near to the source of particles because they're not well mixed in the atmosphere. So here you're close to the source of a freeway, close to the urban region, and you have very, very many more particles. So it's important to recognise the heterogeneity both in the number concentration and the mass loading, and in a temporal sense as well as a spatial sense. So there, going from polluted to clean, you're talking about number concentrations going from 10 million per cc down to the background in Antarctica of about 10 particles per cc. 10 particles per cc is clean. Even in the laboratory, it's very, very hard to get down to numbers as clean as in the South Pole. And the mass concentration going from tens of thousands of microgram per cubic metre down to fractions of a microgram per cubic metre. So when we're talking about the composition of particles, given the number of sources of primary and secondary types and combustion particles, and the way that they're mixed in the atmosphere, you can see that you've got the potential to have really, really complex particles. Even every single particle could contain many, many components. So, whilst in the models, you might say sea salt, sulfate, black carbon, whatever, in reality, you've got this real complexity of mixtures, as we saw from the micrographs earlier on, where you see that you sample using electron microscopy and you see that there are quite a lot of multi-component mixed particles. And here, this is much, much simpler than it really is, because the OC component is just labelled as one component. Does anyone know how many organic compounds there are in the atmosphere? How many different sorts? They think there are of the order of tens of millions of organic compounds in the atmosphere. They can't count them because there are too many, and they can't actually they can see them with different instruments and they can detect them, but they can't actually say what they all are. And they think that there are tens of millions of them. So what do the individual particles look like in terms of composition? Let me just skip over this one. Hang on a second. I've got some slides out of order here. Right. Doesn't matter. I'm jumping the gun here. But anyway. So let's go into detail now about some of the processes of the formation of the gases that give rise to your secondary components. So these are gas phase processes largely. Where does... No, I'm not going to ask that question. Okay. So these are gas phase processes that give rise to the formation of condensed phase products. So the sulfur dioxide plus the hydroxyl radical. So remember where the hydroxyl radical comes from? Anyone? Give me 3 sources of the hydroxyl radical. Somebody's stolen the pens. These pens disappear. Does anybody know the vapour pressure of a pen? They're really high. They're very, very, very volatile. Okay, so I'm going to carry my own pens in future. Right. So the hydroxyl radical can be formed. The primary source of the hydroxyl radical is the photolysis of ozone to O singlet D. The reaction of O singlet D with water vapour produces 2 hydroxyl radicals. HONO. So HONO is nitrous acid in the atmosphere. HONO plus a photon gives you NO plus a hydroxyl radical. Formaldehyde. Formaldehyde plus a photon in the right region, that also gives you hydroxyl radical. So there are a number of ways of forming a hydroxyl radical. SO2, where do we get the SO2 from? Combustion of sulfur-containing fuels. Okay? Eruption of volcanoes. So is sulfate directly emitted from volcanoes as a primary aerosol? Okay, so sulfur dioxide is emitted. So why is sulfur 4 oxidised to sulfur 6 in a volcano plume? It's actually quite complex. It's a lot of heterogeneous reactions that lead to the formation of sulfate from SO2. So it's like combustion. It's very difficult to say whether sulfate is a primary emission or a secondary emission from volcanoes. But it emits a lot of SO2. So SO2 plus the hydroxyl radical plus M. So what sort of reaction is that? It's a termolecular reaction. So it's a pressure-dependent reaction that depends upon M. So that forms HSO2, and the M is conserved. HSO2 reacts with water to give you sulfur trioxide. Sulfur trioxide plus H2O plus M, what sort of reaction is that? Another termolecular reaction, so it's pressure-dependent. And that forms sulfuric acid. So how long does it take for the SO2 to form sulfuric acid in the atmosphere? Anyone? Any ideas? The lifetime is of the order of days, the characteristic timescale. 8 hours to a day. Ammonia wants to be in the particles if there's enough acid. So if you form sulfuric acid and you have lots of ammonia, so where does your ammonia come from? Fertiliser? Where else? Cows and pigs and chickens. Ammonia is a reduced compound, so it comes from guts and anaerobic. It's an anaerobic waste product. So it's urine, faeces, this sort of thing. So ammonia, what other compound can behave like ammonia? With the same sorts of sources. Same sort of sources as ammonia. Any idea? What sort of compounds behave like ammonia? Amines. So there are a lot of amines that are emitted by the same things that emit ammonia. And amines and ammonia can do the same thing. They both neutralise sulfuric acid. And they really, really do want to be together in ammonium sulfate. If there's not quite enough ammonia to fully neutralise the sulfate, or not enough amines to neutralise the sulfate, they'll form ammonium bisulfate. Is ammonium bisulfate neutral, acidic, or basic? Yeah, kind of weak acid. So what you've got is a bunch of secondary reactions. So SO2 plus OH giving you SO3, giving you H2SO4, reacting with primary emissions, that's ammonia or amines, to give you secondary aerosol. So there's secondary oxidation products in the gas phase reacting with primary emissions in the gas phase, giving you secondary aerosol. So sulfates can exist in a number of chemical forms. Sulfuric acid, if there's no ammonia around. Ammonium, so do we know what NH4,3HSO42 is? Letovisite. Doesn't really matter, but there's lots and lots of different chemical forms. Ammonium sulfate, ammonium bisulfate, etc. In environments with low ammonia availability, it's a sulfuric acid. As the ammonia increases, it's converted into all of the potential salts. And you can have lots and lots of mixed salts. So if you've got a lot of nitrate around, then you'll get mixed complex salts. But the secondary products will have that sort of a form. Coming on to the oxidised nitrogen, what did we say earlier about nitric acid? Is it more or less volatile than sulfuric acid? More volatile. So it's less likely to form particles. Okay? But nitric acid plus ammonia can form ammonium nitrate. Nitric acid plus sodium chloride, if it meets sea salt, can form sodium nitrate plus HCl. Is HCl more or less likely to form aerosol than nitric acid? Yeah, it is more volatile. Okay, so if nitric acid meets sea salt, it'll react with it and kick out hydrochloric acid. So again, nitric acid is formed in a termolecular reaction between the hydroxyl radical and NO2 in the same way as SO2 is formed in a termolecular reaction with OH. So what about night times? Nitric acid. How do you form nitric acid at night? If you've got no OH, NO2 reacts with ozone. What's NO3? Does anyone know what the NO3 is? The nitrate radical. Now the nitrate radical is the most powerful oxidant at night time. But the nitrate radical is in equilibrium with N2O5. So the nitrate radical itself reacts with NO2. So the nitrate radical is formed from NO2, but it also reacts with NO2 to be in equilibrium with N2O5. N2O5 reacts with water to form nitric acid in the particles. What happens if it's warmer? So if the temperature goes up on the right, on this pathway at night, there's two things. This reaction here has a backwards unimolecular decomposition. Okay? So here, the N2O5 falls back apart into NO2 and NO3. But also, nitric acid is quite volatile. So if nitric acid is in the particles, it can go into the gas phase if you raise the temperature. So the nitric acid will go down if the temperature goes up. So what we've got, sulfur chemistry, sulfuric acid, ammonia, water system, and nitrogen chemistry, giving you the nitric acid, means that you can have a whole bunch of different electrolytes in solution if you've got watery aerosol. So recently nucleated aerosol tend to have a lot of sulfate because sulfuric acid forms them along with ammonia. Accumulation mode aerosol can have nitrates in them because they won't form the nucleated particles because their vapor pressure isn't sufficiently low. And in the coarse mode aerosol, you can have lots and lots of things that are of primary origin. So sodium chloride, calcium salts from dust, bromide in the sea spray, magnesium salts, bicarbonates, etc. So these are the sorts of things that can give rise to the electrolytes and salts across the different sizes of particle. But I mentioned earlier that you can have tens of millions of organic compounds. So we almost never see particles that are just inorganic. Sulfates, nitrates, chlorides. We almost always see some amount of organic matter. So in addition to the secondary organic components, we have all of the primary components, primary organic components. Where are most of the primary organic components from? If they're in the coarse mode, where do you think the primary organics are mainly from? fungi, biological particles, pollen, spores, these sorts of things. If they're in the finest modes, where are they from? Combustion, if you call those primary. Don't know. Lots of polycyclic aromatics and these sorts of things. But the secondary components are formed from the VOCs. So the VOCs will be oxidised either by the hydroxyl radical, ozone, or at night time by the nitrate radical to form oxygenated organic products which can partition to the particles. So will organic components become less volatile or more volatile as they're oxidised? If you add oxygen molecules, oxygen atoms to a molecule, your vapor pressure goes down. So they become less volatile. If you snap the molecule, so you fragment the molecule, the carbon chain becomes shorter and their vapor pressure increases. So you can become more or less volatile with oxidation. And ultimately, if everything was oxidised, it would go through to carbon dioxide. But on the pathway, you can form a lot of products that can form secondary organic aerosol. So we've got a load of inorganic salts and we've got a load of secondary organic products to add to the primary organic products. So how on earth are we going to measure this? Because we've got a real mess, haven't we? Now, if you suck particles through a filter with a pump, you get a load of particles on a filter. Does anyone know the sorts of analysis you can do to find out about the particles and what they're made of? Have you done analytical chemical techniques at all? So you can do liquid chromatography mass spec or gas chromatography mass spec, capillary electrophoresis mass spec. Do you have any practical classes where you do these sorts of techniques? Have you done any analytical chemistry at all? Well, there's something that maybe we should give you some opportunities for. But what happens if you collect lots and lots of particles and then you put them through a chemical analyzer? What does it tell you about individual particles? It doesn't tell you much about them. Because if, for example, you have sulfate measured at a certain amount, so here 7.2 microgram per cubic metre, you don't know if that's equally spread across all of the particles or just in a few of the particles. So filter techniques lose the individual identity of the components of the individual particles. You can use online direct sampling and measure this and get higher time resolution. This normally takes a few hours to collect a filter sample. But here again, you still lose the information about where the individual components are. So do you understand the limitations of the different sampling techniques? If you collect all the particles onto one filter, you don't know what's in any one particle, you only know what's on the filter. If you directly sample the air, you still don't know what's in the air, what's in individual particles, but you know what's in the air at any given time. So you get better time resolution, but you still don't know what's in any one particle. So the sorts of filter technique results that you get can tell you something like this. So how much mass of an individual component is measured in a different regime. So in the remote marine, you're dominated by sea salt. In the perturbed marine, you've got sea salt and sulfate. In clean continental, you've got some sea salt and sulfate. By the time you get into a polluted environment, you've got a bit of nitrate, etc. So they're the sorts of very, very rough measurements you can get from filters. If you look into more detail, with more detailed chemical analysis, you can find out more about the individual components in different size ranges. So if you look here, has anyone come across a cascade impactor before? So what happens, I need a pen, this is just no good. So if you suck air in here, and you have a plate here, the air will let's just do this. Right, hang on a second. I'm not going to be able to do this. If you suck air in, to an increasingly tightening set of plates, big particles will carry straight on, smaller particles will follow the flow stream line. Increasingly smaller particles, as you close the gaps further and further, will be deposited upon the plates. So you can get different size fractions from cascade impactors, which means that you can get the smallest particles going to the largest particles. So the smallest particles will be deposited here, next smallest there, next smallest there, next smallest there, etc. So that means that you can take filters from a cascade impactor and take them for offline analysis. And these are the sorts of data. So it shows that at different sizes have different particle compositions. So whilst this technique here, if it all goes onto one filter, doesn't tell you anything about what's in individual particles, cascade impactors still don't tell you what's in individual particles, but they do tell you what's in individual size fractions of particles. The most sophisticated sorts of online techniques now can sample, size, vaporize, ionize, and measure, which means that you can start to get direct online measurement of the chemical composition. So this is one of those sorts of instruments that sucks air in, focuses the particles in the air through a series of aerodynamic lenses, and then you can see that there's a slot in a chopper wheel that allows some of the particles to pass through it, so that these particles then move down a vacuum to an oven. Now, if you have a big particle and a small particle, and they're racing through a vacuum to this point here, which one will win? Well, if they're sucked through an orifice there, they both have the same kinetic energy. So the bigger one will have the lowest velocity. So the smaller particles will reach the oven more quickly. So in this instrument here, smallest particles reach this position here more quickly than larger particles. So if you can measure as a function of time what these particles are made of as they are sucked through, you can get the chemical composition as a function of particle size in real time. And even more fancy than those sorts of instruments, if you put something called a time of flight mass spectrometer in here, you can measure the chemical composition at great detail. So instead of the old-fashioned quadrupole, we have a more expensive, more modern time of flight mass spectrometer, and that allows us to measure the particle size as a function of composition, particle composition as a function of size, but with very high resolution of the chemical components. And that's what's needed for separating a lot of these organic components. So what very high resolution time of flight mass spectrometers allow you to separate the mass spectral fingerprints of the chemical, of the different molecules. So that can allow us, for example, to separate out the different fractions of chemical components as shown by that part of the mass spectrum. So these are the sorts of things that allow you to move from the simpler techniques through chemical analysis to online direct sampling with quite high resolution of the chemical components. So these are the sorts of pictures that you can get out from aerosol mass spectrometers as opposed to the filter measurements. So when we were in, I think this was a Korea field project, so we were in South Korea, and we were measuring the amount of water-soluble organic carbon. You see these histograms, they were being made from a 2-stage cascade impactor. So we were measuring the water-soluble carbon with 8-hour time samples. But we also measured organics using an aerosol mass spectrometer. And you can see you get much, much higher time resolution than you get from the long-term, time-integrated impactor samples. So these new toys have allowed us to map out globally the sorts of chemical composition that you can have in the aerosol. So these are in PM1. So this is in particulate material less than 1 micron. So what would you say is the overall picture of the PM1 aerosol composition from that map? I mean, this is 2009, so this was 10 years ago. What it's saying, I think, is one of the take-home messages. About 20 years ago, we didn't even know that there were organic components in most of the aerosol. But the organic components here are shown by the green and grey parts of the pie charts. And you can see that most places that we've been to measure the aerosol particles, you see a significant fraction is made up of organic components. So what we have, so are these organic components, are they primary or secondary? Can instruments tell you if things are primary or secondary? Nope, so we don't know. But what we do know is that you can have secondary inorganic components, sulfur and nitrogen, which can form secondary salts, along with some primary inorganic components there, sodium chloride. That you have some secondary organic components. And we also know now that you have mixtures of the inorganic salts and organic components, which may be primary or may be secondary, and that these are mixed particle populations pretty much everywhere that we go. So going right back to the first slide, where you see those very discrete populations of aerosol, when you actually go to measure what's there in different field locations, you see that there's a very, very complex mixture. Because you're integrating, it's the integral of all of those different sources. And as a function of size, you can see here, this is the size of particles, and these are different chemical components. So the organics, nitrate, and the sulfate can have different sorts of distributions depending upon where you are. Now this is an urban site. What do you think these components here, these organic components of this size, are they more likely to be primary or secondary? It's in an urban site, so it's close to traffic. So it's likely that you're going to have traffic particles, and so they're primary. This remote site was in Jeju-do in Korea, and you can see that all of the components are about the same size. So that's evidence that they're all mixed together in the same sorts of particles. So you know that nitrate is secondary, you know that sulfate is secondary, so there's a good bet that most of your organics are secondary as well. So the idea is that your traffic and primary organic components are separate from your secondary components in an urban site, but that your secondary components are all very, very similar and well mixed by the time you get into a background site. So this now brings us on to this state of mixing. How can we test and how can we tell if different particle components are mixed together? Because we've already, even with fancy toys like this, we're not measuring the individual particles. We're just measuring particles that take the same amount of time to move down a vacuum. So this will be groups of particles of the same size. Doesn't mean they're all made of the same components, because you can see that even at the same size, you've got different components and different shapes of the distributions of the components. So how do we say something about whether the components are mixed, whether the particles are mixed? What we need to do is measure particles by, let me have a look. Right, I'm not going to say anything about how we do that. Right, what I'll do is I'll save that till the next lecture. But what you might consider, if you look at these particles here, that particle there, that particle there, and that particle there may all be roughly the same size. They might all take roughly the same amount of time to get down this mass spectrometer. But you wouldn't know if they all arrive at the oven, if they all arrive at the detector at the same time, whether individual particles are made of the individual components or whether the average composition is mixed across all of the particles. So you need some type of detector that separates the individual particles, or that separates the behaviour of individual particles. We'll come on to discuss some of the properties that allow you to detect that and allow you to describe the particle populations in the atmosphere in the next lecture. But at the moment, you can't just do it by chemical composition. So this summarises roughly what we've said about chemical composition in terms of sources, composition number, size, mixing state, hygroscopicity, how they vary from polluted to remote marine. So these are some of the sorts of characteristics that you might be expected to understand and be able to describe. Okay, so I'll leave you with that slide, which shows a little bit about how the different sorts of aerosol interact in the evolving atmosphere, and gives you a little bit of a picture of the life cycle of the aerosol. So how the different sources contribute to the loading, which are transported in the atmosphere, they're deposited, they're interacting with radiation, interacting with clouds, and they are contributing to the Earth system in that kind of a way. So what you want to do is try to contextualise the composition and the size and the behaviour of the aerosol particles as they're going through that cycle. So, we'll call it a day today. I'm not going to start. No, there's no point in starting on interaction with water. Okay, and next week I won't be here. Next week I'm in India. So, Hugo will be covering for me and doing the next one of the gas phase lectures. And I will be back the week after. There's no lecture that week, is there? I don't think so. Is that week 6? Next week is week 5, is that right? I think week 6 there isn't a lecture scheduled. If you look on the Blackboard site, I think, let me just... I can't remember.
I believe the week after next week, we still have lectures.
I know you have lectures, I'm just trying to work out, and what I've got is... Yeah, in this one. Yeah, 135. Week 6, there will be no class, but problem will be provided for unsupervised practice and solution will be available ahead of week 7 lecture the following week. Right, that was done when I was supposed to be in Indonesia on week 6. I don't think I'm going to be in Indonesia on week 6. I may be able to give you a lecture, so I'll let you all know before then. Okay, so you'll have Hugo next week, and I will let you know whether you've got me the week after or whether there's no lecture. Okay. Cheers. I'll catch you in 2 weeks' time. Ah, I didn't give you the card reader, did I? Too late now. We'll do it next time.